Hi, my name is Adam Boss. For my Choose My Own Adventure, I replicated Galileo's lab, where he dropped two balls of different mass off the Leaning Tower of Pisa, and he proved that they would land at the same time. So I did the same to prove a 400-year-old experiment. So, for the introduction, the purpose of this lab was to prove that all objects on Earth will fall at the same speed, or land at the same time, or experience the same acceleration, net force, etc. It will all be the same. Um, this is all under the assumption there's no wind resistance, which is important later. So the fundamental principles and formulas for this lab are Newton's universal law of gravity, which explains the formula to find the net force, which in itself explains why objects of different mass will fall at the same speed, experience the same kinematics. And Newton's second law, also known as the momentum principle, which just explains why the changes in velocities that the objects experience. Also, you could look this lab from an energy perspective, specifically with kinetic and gravitational energy and how those two interchange based off their formulas. And the result of the lab proved that Galileo's lab, which again is 400 years old, is actually right, believe it or not. So the main physics principles, one, the force for calculating the force of gravity between two objects has a universal gravitational constant, and two masses multiply together, and this explains why they will have experienced the same kinematics, but I'll get to that later. Here you have some kinematic equations. This one right here is pretty indicative of the Newton's second law, or the momentum principle, with acceleration being the net force divided by a mass. Again, this is also G in Earth. And then also you have kinetic energy, which is 1/2 mv squared, and gravitational potential energy. So for the lab itself, we had the system was the two masses of 20 and 100 grams in the Earth, and the surroundings was the rest of the universe. We considered air resistance to be negligible, and we considered the effect of the universe to be negligible, or the masses, or the gravity between the two masses to be negligible, which it really is, etc. These masses were held at 1 meter above the floor. They were released from rest at the same time, and we analyzed the movement specifically in the y direction, because that's where the gravity acts. It doesn't act in the x. So for the code itself, beyond all like the visual stuff, the code explains. For one, you have the momentum principle here, which explains the change in velocity of each ball based on the net force they experience. And the net force was just calculated based off the G, which is acceleration due to gravity on Earth, times the ball. And the fact that these net forces will be divided by the mass, in a sense, cancels it out and gets the same value. So from the kinematic perspective, that explains the difference. Now, also for energy, such as the kinetic and potential energy, you'll see that when kinetic energy and gravitational potential energy are set equal to each other, which they should be in this situation, mass will cancel, which is also indicative as to why the objects will fall at the same speed, because they experience the same net force. Sure, when you have a bigger mass, you will have a larger gravity, force due to gravity, but then again, this will be divided by mass to find the acceleration. So the acceleration and kinematics are the same. Between the model and the real life experiment, we had a very similar results. There's some deviation right here, the 20 gram mass, but other than that, it was pretty uniform. As you can see here, between the two masses, the energies, although like the energy for the 20 gram one, for example, is less, in this y-axis, the overall trends are the same, and the change in energy is still zero. Again, as the mass is irrelevant. Sure, it's important to the total energy, but changes in energy in comparison don't do much. And this straight velocity versus time for both masses is kind of indicative that there's a net force that is constant, or else the velocity would not have a linear relation. So one source of error is wind resistance, and what if. There weren't any what ifs for this experiment, so I came up with some. If it were on a different planet, nothing would change, and if it were a different surface area between the objects with larger surface area would land after, because it's experiencing smaller net force, because there's wind resistance counteracting, which is an assumption we made in our model, or in our real life experience, that there's no air resistance.